Okay. Yes, got it. Got it. All right. So we left off talking about energy changes, heat during certain chemical processes. We looked at enthalpy of reaction, so heat given off by chemical reactions, like our hydrogen balloon example. Depending on how many moles of things we actually combust in that reaction, will change how much product in the terms of heat is produced. So we can do some other calculations here of heat required during certain chemical processes. And one of those is heating water. So everyone in this room has heated water in some sense in lab during that HCal experiment. We were heating different objects, looking at energy transfers. So this heating curve tells us the energy required to either change the temperature or change the phase of water. And so with the different parts of this graph, what I want you to be cognizant of is that we need different calculations. We do different calculations for different parts of the graph. For all of these blue lines, we see as we add heat on our x-axis, we're actually changing the temperature of our sample. So the blue lines, A to B, C to D, E to F, you want to use your Q equals MCAT equation, where M, you have to take into account the mass of your sample and the specific heat of your sample, and being cognizant of the phase. So basically, any added heat that you put into your sample goes into changing the temperature of your sample. So that's why we have this delta T component we have to account for. That's all the blue lines, all right? All the blue lines, Q, heat goes into changing the temperature of your sample. But the red lines here, these lines, you see that with added heat, you're not changing the temperature of your sample. All the added heat that you're adding to your sample is actually changing the phase of your sample. So we don't want to use Q equals MCAT. We actually want to use enthalpy of vaporization or fusion, depending on what phase change it is. So these, I've highlighted them pink now. We actually want to use the enthalpies of those phase changes instead. So note how this equation has no delta T term in it. And that's because, again, the heat added to the reaction or to your sample goes to changing the phase, not the temperature of your sample. All the added energy is basically changing the attractions particles have to one another. So this little kind of side question here, you can see the enthalpies of fusion and vaporization for water, and you see for vaporization of water, it's a lot higher. It takes a lot more energy to vaporize water than it is to melt it. Why do we think that is? Why does it take a lot more energy to turn a liquid to a gas versus a solid to a liquid? What do we think? Think about attractions. So the idea here is vaporization is actually always requires more energy than fusion. Think about how much you have to pull the particles apart, right? Vaporization, you're turning a liquid to a gas. You're separating those particles infinitely far apart. That's going to take a lot of energy. Versus fusion, when you turn something from a solid to a liquid, do you break all of the intermolecular forces? No, you only break some of them. So that's why that value is smaller. Yes. Okay. But they're both positive values. So this would be solid to liquid. You're not breaking all of the intermoleculars. Okay. So we can do some calculations. Just make sure you're using the right equation. Q equals MCAT versus your enthalpy value. So here, how much energy is required to melt 275 grams of solid ice to liquid water at 0 degrees Celsius. So see how this is happening at one temperature. So we are just looking at the phase change. We are looking at the enthalpy of fusion for this process because we're turning a solid to a liquid. And this will be a positive number because we are adding heat to the system. So the only problem here is that the enthalpy value is given in moles, but the amount of substance I'm working with is in grams. So I need to turn that 275 gram amount to moles first. But I even give you the molar mass of water. So that's nice. We haven't done one of these in a long time. All right, so 275 grams of water is equal to like 15, where is it? Okay, yeah, 15.26 moles of water. That's how much water I have in this sample. So now that I have the mole amount of water, I can use the enthalpy value that's given here that it requires 6 6.02 kilojoules of energy per mole of water to, what are we doing? We're melting it for delta H of fusion. So 1 mole on the bottom, 6.02 up top kilojoules, because that's per 1 mole, multiply by the moles I actually have, and you get that it requires 91 or 92 kilojoules of energy to melt that amount of water, right? From a solid to a liquid at 0 degrees Celsius. We just take into account that enthalpy value. So that one's a pretty straightforward question. We can go through more of our heating curve, right? More of our heating curve if we're given a starting temperature in a phase and have a final destination, a final temperature and phase. So in this question, we want to turn 15 degree like room temperature water, but we want to turn it to 100 degrees steam. So thinking about stepwise, what parts of the heating curve do we have to go through? We're starting at like a liquid regime. So somewhere, like over, where's liquid? Where's liquid? Somewhere here. So somewhere like liquid water, like right here. And we're adding heat to increase the temperature. And then we're adding more heat to convert it all to steam. So we need to add up, determine what is the energy of both of those legs, and then add them together. So here are the different steps. Turning the liquid at 15 degrees Celsius to 100 degrees Celsius. This is Q equals MCAT. Right? Where delta T in this case is what? What value is delta T? 85 degrees. We're heating it up 85 degrees. I think that's like the obvious thing here. You see, oh, we're changing the temperature. We need an equation that accounts for that change of temperature. Q equals MCAT, right? It's liquid water, so do make sure you're using the correct specific heat of liquid water, that the different phases of water have different specific heats. Then the second leg that we're calculating is turning the liquid water at 100 degrees to steam, so a gas at 100 degrees. So this is where we take into account the enthalpy of vaporization. Both of those are happening in 2 different steps. So we're doing 2 different calculations and then adding those 2 steps up. So that let's do the first one, the one in green first. The heat required to just heat up the water to 100 degrees. So mass, 275 grams, specific heat, 4.184 grams per gram, joules per gram degree Celsius. And our delta T, we're heating at 85 degrees. All right, and that requires some amount of energy, actually a lot of energy, because again, water is really hard to heat. 97800 joules or something like that. That's just the heat required to just raise the temperature of the water to the boiling point of water. And now we need to account for the enthalpy of vaporization. So I'm going to use that same mole amount that I got before because it's the same mass. So 15.6 moles of water times the enthalpy of vaporization. So what value do we want to use? So let's look at these 2 values up here. So do make sure you're using the right one. Are we going to use the 6 kilojoules or the 40? 6 or 40? 40, yes, because we're vaporizing it. We're turning it from a liquid to a gas. So we're using the vaporization one, right? So 1 mole, it costs me 40.7 kilojoules to heat that up, or sorry, to turn that into steam. And so that costs me 621 kilojoules of energy, all right? And then if you add those 2 numbers up, so this is 97.8 kilojoules. So add those 2 numbers up, you get that the total energy required is 719. Right, so there's some small details here with these calculations. Q equals MCAT requires specific heat and the mass of the sample, but the enthalpy of vaporization, we need the mole amount of the sample. So you have to do some conversions to get those 2 energy values before you can't add them up. All right. So this strategy was quite simple. It was just 2 steps, but in theory, you should be able to, if I gave you a starting an amount of liquid, you could start at, some temperature of solid ice, heat it up, melt it, heat up the liquid, boil it, heat up the steam. You could calculate every single step, right? Add up all of those heat steps and add them up to calculate the heat required for that entire process. So you would just have to either Q equals MCAT each of these blue steps, or use enthalpy for those flat steps. All right, so you just have to think, okay, how do I get from here to here? And the separate steps, use the appropriate specific heats or vaporizations. All right, so that's calculations. That's like, I guess, as hard as it really gets, which isn't that bad. All right, so let's talk about some other ways we can use enthalpy and calculate enthalpies of reactions. It's not really feasible to do every, single reaction on a benchtop. Sometimes we want to use, maybe table values to calculate enthalpies of reactions. So if we have known reactions, we have reactions where we have a known enthalpy of, so like I know a certain amount of heat given off by a reaction, we can actually add up different reactions with known heats, add them up to get a new reaction. We can add them up, get a new reaction, get a new heat. All right, so this is like a kind of like a fun puzzle. This is called Hess's law, that it doesn't matter the steps you take to get from reactants to products, as long as the individual steps add up to where you want to go. The energy value, the energy change is still the same. So that's called a state function, where only the initial and final, your initial and final, where you start and where you end, as long as those are the same, the energy change will always be the same. So for example, here, enthalpies and changes in internal energy are state functions, but things like heat and work are not. Sorry, not heat, but just work is not a state function. So the path is, with those energy values, they are path dependent, while these ones are not path dependent. So the whole strategy here is we can piece together small reactions to give us an overall reaction. So the strategy here is you want to look at the given reactions and match them with your target reaction, the reaction we want. And so making sure if we change the direction of a given reaction, we need to multiply the enthalpy of that step. If we have to multiply a reaction by a coefficient to get the coefficients to match, we have to do the same to that delta H of that step. In words, it's kind of confusing. It's better to just do the puzzle and you'll see how it works. Yeah. X, yes, it's times a -1. So if you flip a reaction, you flip the sign of delta H times -1. Yeah. I don't know how, yeah. So how can I make that more clear? Times -1. Does that make, is that, yeah? Okay. All right. So yeah. And so the whole goal here is to get your overall reaction to match your target reaction. A side note here, if you add up your reaction and a substance shows up on the reactants and the product side, they cancel out. So here, for example, if I, add up my reactions and I got A plus B gives me A plus C, those two A's cancel because they're on each side, and the overall reaction would be B gives us C. So that's how we get things to cancel if you have them on opposite sides. Or if we have 2x plus y gives us x plus z squared, what term can cancel here? What term? How many x's? Just one of them. Yeah, so we can only cancel one of those x's there. All right, okay, let's do the puzzle. Here are my two reactions. They have known enthalpies. What's the enthalpy change for this guy? These are fun. They're like puzzles. So this is my target reaction, all right? And I get to play with the other two reactions to try to get that target reaction. So I'll focus on one substance at a time. I'll ask myself, in which reaction is that thing? AB2. In which reaction does that show up? Reaction, where is it? 1. Yes, it's in reaction 1. Then I ask myself, is it on the right side? Is it on the right side in reaction 1? No, it's on the product side in reaction 1. Where do I want it? I want it in the target reaction. AB2 is on the product, or sorry, the reactant side. So how can I get AB2 to go on the reactant side? Flip the reaction. All right, so I want to flip the whole reaction. But if I flip it, what do I have to do to delta H? I have to multiply by -1, that delta H value. All right, so if we flip a reaction, we flip the sign of delta H. So let's just rewrite that. Let's not rewrite it yet. Okay, so I've flipped AB2 to get it on the reactant side, to switch the places of products and reactants. But I also need to ask myself, is it in the right quantity as well? Do I have the right number of AB2s? No, I don't, because there's 2 in my target reaction, but only 1 in my given reaction. So in addition to flipping it, I also want to multiply this reaction by 2 as well. So if I multiply the whole reaction by 2, what do I do to enthalpy? Also multiply by 2. So I'm going to rewrite reaction 1 that is flipped and times 2, just so I can clearly see, you know, what I'm dealing with. So I have 2 ABs, give me 2 A's plus 4 B's. And so I'll write the new delta H value is going to be that negative 35 kilojoules number, but I need to multiply it by negative 2 because I flipped it and I multiplied it by 2. So flipping it gives it, changes the sign. So there's the negative, and then times 2, the times 2 here. Okay. Oh, wait. So AB2, sorry. All right. So there's that. Now let's focus on something else. Again, I like to focus on something weird that usually only shows up in one spot. Let's focus on A2B5. Which reaction does that show up in? The second one. Do I have to, is it on the right side? Is A2B5 on the right side? Yes. Is it in the right number? Yes. So do I have to change anything about it? No. I'm just going to add reaction 2 as is. I'm not going to touch it. I'm not going to make any changes, but I will rewrite it. 5B gives us A2B5. I'm just going to rewrite it as is, so I see how the reactions add up. And so since I just added it as is, I don't have to change that enthalpy value. All right, so let's add up these 2 reactions and see what cancels. Okay, what terms can cancel? These A values can cancel, and then the B values can cancel, but do all of them cancel? No, just 4 of them will cancel. All right, so that becomes a 1. All right, so I'll just lightly cross these out so you can still see them. All right, that the A's cancel and 4 of the B's cancel. So then we can see that the overall reaction is 2AB, 2 of them, plus a B gives us A2B5. That reaction, is that my target reaction? Is that what I wanted all along? Yes, it is. Okay, great. So since I've like verified that, you know, manipulating these given reactions give us the target reactions, now I can go ahead and add up those enthalpies that I also manipulated. So remember, we had to change these enthalpy values. So I can do that math, right? So the first enthalpy is positive 70 kilojoules plus negative 90 kilojoules will give us negative 20 kilojoules. So we add up those manipulated enthalpies. So it's just, you know, kind of like a puzzle here. Yeah. It doesn't matter what side it's on. Correct. Yeah. As long as you have, you know, at least one on the product side, one on the reactant side, it doesn't matter. So the step I skipped is I really should combine both of these reactions so they're all in one line. They're all in one line, and you would see, oh, okay, we have 2 A's on the reactants and on the products. I can cancel them out. Does that make sense? Okay, let's just do another one. Okay, this one's a little harder because there's 3 reactions. Okay, I like to, again, focus on one thing at a time. So I asked myself, where does carbon show up? Which reaction? Reaction 2, yes. Reaction 2. Is the carbon on the right side? Yes. Is it in the right number? No. So what should I do? Multiply the whole thing by 2. Okay, great. All right, next is hydrogen. Do be careful. Sometimes certain substances will show up in more than one reaction. If that's the case, skip it. Skip it and hope there's another like reactant you can focus on to get you closer to the answer. But in this case, hydrogen actually only shows up in one reaction. It's right here, I think. Yes. All right. And so I see that. Is it in the right side? Yes. Is it in the right number? Yes. So I'm going to just do nothing to that reaction. I'm just going to leave it as is. I'm going to just add it as is because that hydrogen's on the right side. And so the last one here, C2H2 shows up in reaction 1. Of course, that's the only one left. Is C2H2 on the right side? No, it's not. So I'm going to flip the reaction. So flip it. All right. And so there we go. And then see how there's like a bunch of oxygens and waters around. If we would do these manipulations and actually cancel out the leftover things, we should be able to see that the oxygens cancel out, the CO2s cancel out, and the waters cancel out, and we're only left with these different substances. So the whole idea here is we identified what manipulations we need to do to enthalpy, so we can just go ahead and add up those enthalpies the same way we manipulated it. So adding those up, we have 1,300 kilojoules. And then we're subtracting 2 times negative 394 kilojoules. I can't do that in my head. And then we're just going to subtract 286 kilojoules. Add that number as is, because we did not do any changes to reaction 1. Can you do that in your head? And so you should get this number, 226 kilojoules is the enthalpy of that target reaction. Right? Okay. So in this step, you can go through the steps of, writing all of the manipulated reactions and watch all of those oxygen, CO2s, and waters cancel out. They should cancel out. But I don't feel like doing it. All right. So just trust me. Okay. All right. So those are Hess's laws, taking known reactions and just manipulating them and adding up those enthalpies to get a new enthalpy. So we can figure out the enthalpy of a reaction without actually doing it, without actually measuring it. That's kind of nice. All right. The nice thing about thermodynamics and how that works. All right. And so one of the last ways we will inspect enthalpy numerically to figure out how to calculate enthalpy through table values, that is standard formation reactions. There are known table values of energies of substances. And if we know a balanced chemical reaction, we can compare those table values and estimate what the enthalpy of the full chemical reaction is based on formation values. So these are literature table values that you can always look up. So again, enthalpy of a reaction is a state function. So enthalpy of formations, we can use this to calculate that enthalpy of reaction, because it doesn't matter the path we take, as long as where we begin and where we end is exactly what we want, the energy change should still be the same. So the definition of a formation, enthalpy of formation, it's the energy required to form 1 mole of a substance from its elements in its most stable state. Right. So here are some examples of elements in their most stable state. So oxygen gas, diatomic nitrogen gas, carbon in its most stable state is a solid, but actually in the form of graphite. So graphite is more stable than diamond. So diamonds are not forever. Graphite is. Okay. Zinc solid. So all of like the metals on the periodic table, the solid form is their most stable state, and etc. So the definition of all of these substances, these actually have formation values of 0 kilojoules per mole, that we've just set the reference point that these elements are in their most stable state. They're 0, they contain like 0 energy, I guess, right? 0 enthalpy within them. So basically we can form any substance, given here methane, we can form methane from its elements in its most stable state, and calculate, okay, given where we start, we have the most stable state. If we want to form methane, that's either going to produce or require a little bit of energy, depending on the relative energy of that product. So how we write a enthalpy of formation for a substance is you need to just inspect each element in your compound, right? You want to form 1 mole of this, okay, exactly 1 mole of this, but from the elements in their most stable state. So you just need to ask yourself, okay, carbon is what in its most stable state? Like what state? Solid, but it has to be graphite. Okay. And then you also need to balance it. So just 1 carbon is fine. So then we move on to hydrogen. We need hydrogen in its most stable state. What do you think hydrogen is in its most stable state? Stupid pen. Yes, it's H2. H2 gas. Yes. Is that balanced? No, I need a 2 in front of that hydrogen. So this reaction that we just wrote is the delta H of formation of methane. And this you could look, methane gas, okay, specifically. So you can look up this value. You can look at a formation table, and it will have next to the word methane, it will give a formation value of some value, of like some number. You just need to know what that value means. It means this reaction requires or will give off the amount of energy listed in the table. I think the next page, yes, has some formation values. Yes, so let's look it up. Is it on here? Did I put it on here? Is it on here? What? It's not. Okay, it doesn't matter. Let's just look at like CCl4. All right, if you look at that gas, see, same idea here. If you look up the formation value of that substance, you'll see, okay, the formation reaction for that substance will give off 103 kilojoules of energy. That's what that means. But we need to know it comes from this reaction that's taking place, taking solid graphite, adding 2 moles of, I guess in this case would be chlorine gas, to give you 1 mole of that product. It has this enthalpy value. All right. So that's what these table values mean. All right. The energy to form these specific substances. So let's write the balanced chemical equation for the formation of liquid ethanol at standard conditions. So let's remind ourselves how to do this. Liquid ethanol, it needs to be the product. So C2H5OH. Liquid state is important too. With formation values, the state is just as important. All right, now we just go through all the elements again. Carbon in its most stable state is solid and it's graphite. But it's, how many carbons do I need? 2. All right, I have some hydrogens. All right, I have some hydrogens, a total of 6 hydrogens I need to account for. So I know hydrogen is a gas in its most stable state. So how many moles, what's the coefficient in front of hydrogen here? 3, because I need 6 hydrogens on the product side. And then lastly, I have oxygen. What is oxygen in its most stable state? O2, also a gas, great. So at this point, you might be thinking, oh, there's only 1 oxygen in the product. Okay, so if I put a 1/2, I need to multiply everything by 2 because we don't want coefficients, or sorry, fractional coefficients. But with formation reactions, it is absolutely okay to have a fraction. You actually need the fraction there. So we're actually going to put a 1/2 in front of O2, and it's going to stay there because the definition of a formation value is the amount of energy it takes to form 1 mole of this product. And yes, that will require 1/2 mole of oxygen to do that. So we don't want to get rid of this fraction by multiplying everything by 2, because if we do, then we'll have a 2 coefficient in front of the product, and then that's no longer a formation value. So we'll keep the fraction. Fractions are absolutely okay with formations. Okay, and so that's the reaction. We can look up the enthalpy of this reaction. This lives in books. You can look it up, right? For the specific reaction. You don't actually have to do it. Where is it? It is right. Is it negative 277 or is it negative 235? What value is it? 77 or 35? It's the 77, yes, because again, phase is just as important. I said the formation of ethanol liquid, not of the gas. So see how it's a different energy value if the product is different, right? Again, because enthalpy is a state function. The energy of your product absolutely matters. A liquid is different than a gas. So yes, our formation for this reaction we just wrote is negative 277.7 kilojoules. Oops, sorry. All right, so let's practice a bit more writing formation reactions, okay? Again, here's some 3 substances. Let's write their formation reactions. The strategy here is this needs to be the product, and you need to form 1 mole of it from its elements in its most stable state. So N2CO3 solid, that's my product. And I need to determine, okay, what is sodium in its most stable state? It's a metal, so it's a solid. And we just need 1 of them. Oh no, we need 2 of them, sorry, there's 2. Okay. Carbon in its most stable state, graphite again. All right, and then lastly here we have oxygen. So we know oxygen is O2 gas, but what is the coefficient in front of O2 that we need? How many oxygens do we need on the other side? We need 3, so we're actually going to put a 3/2 in front of oxygen. And we're leaving that at that fraction. That's completely okay. Okay, so let's keep going. Ammonium chloride. So the idea here is that ammonium chloride needs to be the product. And we form everything, all its elements from its most stable state. So nitrogen is N2 and a gas. But what's the coefficient in front of nitrogen that we need? 1/2. Yes. Okay. Because we just want 1 nitrogen atom. And then hydrogen, I think we need 2 hydrogen gases. And then we have chlorine. So chlorine in its most stable state is Cl2, and that is a gas. And then what's the coefficient in front of chlorine? 1/2, because we just want 1 chlorine atom. Great. And again, these 2 reactions, you can just look up. You can look up on a table, and then you can exactly know the enthalpy of this reaction. All right, the last one. This one's tricky. So O2 is the product. What's the reactant? What's oxygen in its most stable state? O2, yeah, O2 gas. Huh, interesting. Okay. Do we know the energy change of this reaction that I just wrote, this last one? 0, yes. So the delta H of formation of this reaction will be 0. How do you know? Yeah, nothing happens. Yeah, so the energy change is 0. Remember what I said, anything that is already in its standard state, or sorry, most stable state, it has a formation value of 0. All right, so that is something you need to know. You will never find diatomic oxygen on a table, all right, on a formation table. Why? Because it's already in its most stable state. It's implied that it has a formation of 0. Versus other oxygen containing compounds will have non-zero numbers. All right. So we would be able to look up the values for these 2, but not for the last one. So don't let that fool you. Okay. Because this is the last way that we can calculate enthalpies of reactions is using these table values, okay? Utilizing the fact that enthalpy is a state function, that it just matters, you know, where we start and where we end, and that's how we can calculate the energy difference. So if I know the energies, the relative, you know, formation values of our products and the relative formation values of our reactants, I can just look at that energy difference and figure out the overall energy difference for the total reaction, right? So this is I guess the last equation we can use to calculate enthalpy of a reaction. If you sum up all of the formations of the products and sum up all of the formation of the reactants, subtract them, that's the enthalpy of the overall reaction, right? The tricky thing here is that formation values are oftentimes negative. We're subtracting a number, so there's a lot of negative signs floating around. So do take your time with these calculations. You don't want to mess up by a negative sign, right? So I like to assign formation values to all of the reactions, the reactants and products, and sum up the formations of each of the sides. So at this point, you should just memorize that the enthalpy of a reaction is just products minus reactants, and we need to take into account coefficients here. So methane, I give you the formation of methane, it's negative 74.8. All right, CO2 is negative 393.5. And then what is the formation of water? Which one do we want to use? 285 or 241? 285, yes, because in the reaction it's a liquid, so I need to make sure I use the liquid one. So this one is negative 285. So do make sure you take into account coefficients here. So since there's 2 water molecules, I want to actually multiply that formation value by 2. And I'm just going to sum up both sides. Oh, actually, there's one I forgot. Where's oxygen? Where's oxygen? I forgot that one. Did I not give you enough information to solve this? What should you know about oxygen? It has a formation of 0 because oxygen is already in its most stable state. Okay, so don't let that fool you, okay, that I didn't include oxygen in this table. You should know that it's already stable. It has a 0 formation value. All right, and so we can add these up. So I see that the total enthalpy of the reactants is 74.8 kilojoules, and then the sum of the products, well, maybe not here. Did I add these up for you? No, I didn't. Did I even bring a calculator? I can't do that in my head. And yes, there's a lot of negative signs going around here, so do be careful. I like to separate it in steps because I'm not very smart. All right, so just the sum of the products is negative 965 kilojoules. All right, and I like to just memorize that these table values, it's when you use them, it's always products minus reactants. So I'm going to do negative 965 minus negative 74.8. See, there's like there's minus negatives. Yeah, there's a lot of places to go wrong. So again, I like to just sum up each side separately and then bring them together at the end. Right. And so this is neat. We don't even have to do this reaction. We can just use table values to figure out the energy of the overall reaction. We don't even have to do it. Okay, so let's do another one. Given this data, let's calculate the formation of C2H5F. So it sounds like we're calculating the formation value of a product, right? Now I give you the enthalpy of the whole reaction. So we know what products minus reactants equals. We're just setting something equal as an unknown. So I still go about this the exact same way. I assign the correct enthalpy formation values to the correct substances. So we're solving for C2H5F. There's HF. So I'll put those in here. So HF is negative 272.6. C2H6 is negative 84. And F2, oh, I didn't give you F2. I have two unknowns. Is that right? What's the enthalpy value of? Yes, it's 0. It is 0. Great. But so what we are solving for is C2H5F. That is what we are solving for. All right. And so enthalpy of reactions are always products minus reactants. So we just, do that. So products here is the sum of our products, and then there is our reactants. So setting up the equation, it's going to be X minus 272.6. Those are my products minus the sum of the reactants. So negative 84 equals the enthalpy of the overall reaction, which I give, it's right here. It's negative 469.3 kilojoules. Okay, lots of negative signs. Don't mess it up. All right, because then that becomes a plus. And then you can do the math. Oh, I already have the answer, but let's just make sure that my answer is right. Negative 272.6 plus 84. So X minus 189 equals negative 469.3. And so you add 189 to both sides. Is that right? Plus 189. Oop. Yeah, negative. So X equals negative 280 kilojoules per mole. All right. So again, enthalpy from these table values, products minus reactants, assign things to their correct places, apply the coefficients, be on the lookout for things already in their standard state. All right. So that's enthalpy. I mentioned if there's time, there's one more type of enthalpy calculation. I'm just going to talk about it briefly because I like to talk about this, but I'm not going to ever assess you on it. Yes. Are they sig figs? Yes, there should be sig figs here. I should have one more. The reason there should be one more is because all of these go out to at least the first decimal place. So since it's all just addition, subtraction, I should be able to go out to one more decimal place here. I was just being lazy. So my answer that I have circled here is correct, but the work I did on my calculator, I was lazy. Okay. Okay, good. All right. What? Can I grade you on sig figs on the exam?
I'm just asking.
Can I?
It's fair.
I'm just saying, like, can I grade on sig figs will I give you the option? All right, unless it says to the correct sig figs. All right. And that was basically chapters like 1 and 2 questions. All right. Yeah. I'm usually never going to give you the option like choosing from 0.1, like 0.1 and like 1.0. Like I would never give those 2 options. That would be evil. That would be evil. All right. No, I care more that you know the concepts, unless I am assessing you on sig figs, where I will say report to the correct number of sig figs. And then yes, I will come down hard on you. And I will put the trick answer, the mistake that most people do. I will put that in there as well. Okay. All right. So energy of reactions. There's one more way we can predict and estimate the energy of a total chemical reaction, and that's using bond strengths. Remember in the last one, when we talked about bond order, right? What was the trend? As bond order increased, as we went from single, double, triple bonds, what happened? Strength did what? Increased, but length decreased. Yes. So what we see, all right, with using bond enthalpies is that the energy of a bonds are really, we can actually look up bond enthalpies, all right? So energies to break bonds. You can look up a delta H value for a bond. That delta H values for bonds are large if the bond is strong or it is short, or both, okay? So basically that means, okay, large bond order bonds, they contain a lot of energy, right? It takes a lot of energy to break them. And so here's a table of bond enthalpies, all right, for different bonds. You see, okay, here's a carbon single bond, double bond, the strength goes up, right? Just like our trend, right? And what I want you to recall, what I said before, breaking a bond, when you break a bond, you separate atoms. So you separate attracted atoms, that's a positive energy. So breaking a bond always requires energy. Making a bond always releases energy because you're bringing 2 attracted atoms together, always. Breaking a bond always requires energy. Got to put energy into the system. Making a bond, all right, bringing 2 attracted particles releases energy, always, okay? So we can actually use Hess's law to predict reactions of overall enthalpies of overall reactions if we keep track of what bonds do we have to make and break to make products and reactants. It's kind of fun. It's like playing with Legos here. So I have these molecules. I have CH4 and chlorine in my products. Basically, what am I doing overall? I'm swapping a hydrogen for a chlorine atom, right? So in order to turn this picture into this picture, pretend like you're playing with Legos. I'm breaking those 2 bonds. I have to break a chlorine-chlorine bond. I have to break a carbon-hydrogen bond. And I need to form 2 new bonds on the product side, right? A carbon-chlorine bond and a hydrogen-chlorine bond. And so we can look up bond enthalpies for these, understand, okay, breaking bonds always requires energy. Forming bonds or making bonds always releases energy. So we can just add up those 2 steps, just like Hess's law, and we can get the energy of an overall reaction. And then I have that right there. All right, so this is the last way you can estimate a enthalpy of a reaction. You can also like take a reaction like this and you can break every single bond on the reactant side. That requires energy. You can make every single bond on the product side. That releases energy. Add up those 2 values. That gives you the enthalpy of the entire reaction. Right? So remember, breaking bonds is at a positive or negative energy value. Breaking. Positive, yes. So your breaking is positive, those numbers. When you make a chemical bond, it always releases energy. So that's a negative value. All right, that's when you make. Okay, so keep that in mind, because there's a misconception that has been thrown around for way too long. Yes. Yes. 1 second. Yes. Because this misconception has been thrown around too long, and I think it screwed up a lot of bio people. All right. When talking about potential energy and chemical bonds, if you look at like any high school textbook, it'll say energy is stored in chemical bonds. Do you remember them saying that? Energy is stored in chemical bonds. It's, I guess, true, but kind of too simple. All right. So here's an example. ATP. This is like where your energy is stored in your cells in order to, save energy to use at a later time. So I found these slides from a high school teacher, Mrs. Smith. So I'm just gonna clown her for a while here. All right. She says that ATP, this is what ATP looks like, adenosine triphosphate, that, this molecule stores energy to be used for a later time. So what Mrs. Smith says is that, okay, ATP, there's 3 phosphates there. What the cell does when it wants energy is it breaks that bond and energy is released. What did we just say about breaking a bond? Breaking bonds always requires energy. So is this correct? No, it's not. It's not. It's a little too simple. All right. What it's actually neglecting, and there's something more subtle about it, okay, is yes, we break off a phosphate off of ATP. But the reason we get energy out, energy is released, is because the bonds we make in the products are much more stable. They're much stronger. Because remember, when we calculate the enthalpy of a reaction using bond enthalpies, it's the strength of the bonds that are broken minus the bonds that are formed. So we're breaking weak bonds, and we're making really, really strong bonds. All right. So this is the correct way to think about ATP and ADP synthase, where those phosphates pop off and energy is released, so to speak. But the reason is because the bonds that we're breaking in the triphosphate, they're relatively weak. And when we form the product, where now we have this free phosphate and this diphosphate group, this is much more stable, contains much stronger bonds than the original form. And it's this overall reaction. What is this? Where we start at a higher energy, go to a lower energy. This is exothermic. And the reason it's exothermic is because the bonds we make are stronger in the products, right? And Mrs. Smith, she ignored that. She just says, oh, you break off an ATP, energy is released. But the subtlety there is because the bonds we make in the products are much stronger. It always requires energy to break something. So in high school, they neglected the forming. You also form bonds in the products. And now you're smarter for it, right? And so here's another way to look at it, right? You start with ATP, you go to ATP. This overall process is exothermic. It'll give off energy, but you still have to give a little bit of energy to break that initial ATP bond to get it going, right? But then the overall process is exothermic. You release a lot of energy because those bonds are so strong. And I'm very passionate about that because that messed me up for a long time. All right, then I was like confused about science. I was like, well, why are we breaking bonds to an ATP, ADP, but breaking bonds are always endothermic? And I was real confused. And biologists, they're not good at explaining those subtleties. But you guys, because you're very intuitive with science, are good. All right, do you ever think about it that way? No? Did you always just think like, oh yeah, you break an ATP, or yeah, it's get energy, free energy? No, you got to think about what's formed as well. Okay, so that's my soapbox. I don't know if you think it's interesting, but I do. I just like to clown Mrs. Smith, whoever that is. Okay, all right, so that's the first law of thermodynamics. Let's talk about the, what? How much money? I don't know. How long did that take? Like 40 minutes? 50 minutes? Okay, so we'll keep going. Second law. All right, so we can all congratulate ourselves. We made it through 1210. We're done with chemistry 1210. You don't sound excited. We did chemistry 1210 in 9 weeks. Yep, yippee. Yeah, we threw out all that stuff you didn't need. We didn't talk about hybridization or MO theory because you don't need it. All right, so we're going to move on to the second law of thermodynamics, entropy. This is where Chem 1220 starts. I like Chem 1220. I think the labs are really fun. These are Matt's favorite labs to do. Yes, we do bar. When we come back from spring break. So do make sure that you read the lab manual very, very well in the discussion when you come back for bar. So 1220 starts here. Okay, so again, be very cognizant of the sign. heat of reaction or enthalpy of reaction, what does the positive negative sign imply? That's, again, super important in this chapter. So the second law of thermodynamics surrounds spontaneity, why chemical reactions happen at all. We'll talk about entropy and look at some more calculations on how we can predict whether a reaction will happen or not. So I bring back my fun meme here. We were in the very tame first law of thermodynamics, where energy lost, negative Q was just gained somewhere else, right? It was very just intuitive. Energy lost, gained somewhere else, all right? Where we just Q equal MCAT both sides, okay? Now we are here with the second law of thermodynamics and entropy. It gets a little bit more chaotic. And so if you know anything about entropy, okay, people talk about it in terms of disorder. Who's heard that before? Oh, entropy is disorder. Entropy is randomness. That's how they define it. It's kind of wrong, but that's my job to tell you why everything you've learned is wrong. So I'll just kind of poke the boundaries of that definition to show you a more appropriate definition of entropy that uses statistical mechanics. But we're not going to do anything fancy, I promise. Okay, but then we'll still return to the idea of heats of reaction, right? Exothermic is what sign? Exothermic implies a sign of a negative, and endothermic, positive. Okay, we need to know these things like that. Okay, so exothermic means that the reaction is losing heat. Endothermic, the reaction or the system is gaining heat. And then finally, we will relate both of these things to Gibbs free energy. So it's a more inclusive and comprehensive term to predict spontaneity at different temperatures. Okay, and chapter 10 has one homework set, but it's really long because it's a lot of math. Okay, so what is a spontaneous process? Why do we care? So if we think about like what spontaneous means, it means that something will happen without continuous input from us, all right? We don't have to continually supply energy to keep a reaction going. Once you start a fire, right, it keeps going, right? As long as you keep throwing firewood on the thing, it keeps going. You don't have to keep reigniting it unless your wood really sucks. But that's a spontaneous process once it's going. Same thing with this, like, will an object heat up or cool down depending on its conditions? So for example, here we have a hot water tank and cold water tank. Our intuition says, oh, heat will transfer, left from right here. You will end up with two tanks that are just slightly warm, right, over time. Or, will a chemical reaction take place at a certain temperature? Will a phase change occur at a certain temperature? Will a precipitate form? These are all the things that we can, predict. Are they spontaneous or not? So we are looking at chemical reactions that are spontaneous. So these are irreversible processes, meaning that in order to, make the reaction go in the reverse direction, you have to supply energy to some degree into it. So it can only go in one direction. Whereas reversible processes, these are isothermal processes where they are reversible. This is outside the scope of this class. We're actually just going to talk about irreversible processes. So we're not going to talk about this outside the scope of this class. All right. And so all of these things relate to entropy and how energy is dispersed in our system. So that's kind of the subtleties we're looking at in these reactions. All right. So again, first law of thermodynamics, we talked about enthalpy, usually heats of reactions, exothermic, endothermic. Did the cup heat up? Did it cool down? Things like that, right? Where we were able to utilize the idea that the total energy of the universe never changes. So if we are just really clever on how we assign system and surroundings, we can utilize, okay, heat lost somewhere is gained somewhere else. That was chapter 9. You don't need to write anything down. We already went over that, okay? What the second law of thermodynamics allows us to predict whether reactions happen or not. So up until now, you just trusted me that these reactions happened when I wrote them on a thing. right? We just trusted it. When I blow up the hydrogen balloon, you cover your ears because you know the reaction's going to happen because it is spontaneous at this temperature and pressure. But that hydrogen balloon reaction is not always spontaneous at all temperatures. It is quite hot in this room. I didn't order the balloon, but there might be some theoretical temperature that hydrogen balloon reaction is not spontaneous. And I put the lighter to it and it doesn't blow up. It might be today because it is very hot, but I'm wearing a wool blazer. That's my fault. Okay. So this is the second law allows us to predict whether it'll happen or not. So the second law says that for a spontaneous and irreversible reaction, okay, they're synonymous. That's what we're studying here. The entropy of the universe must increase. That's the second law, okay, of the universe. So remember what the universe is. The universe is the system, so the thing we're studying, the chemical reaction, and also the surroundings. That's the universe. So we can define the sum, the entropy of the universe as the sum of the entropy of the system. That's something we can like inspect about our reaction, and the entropy of the surroundings, all right? The change in entropy of the surroundings. That's something that we can measure, all right? So that's the second law, that a reaction will be spontaneous if that delta, the entropy of the universe increases. And so me, as a budding, scientist in my youth trying to sound cool, there's this book by H.G. Wells called The Time Machine, where entropy is one of its themes, okay? So again, a lot of folks, they attribute entropy as disorder, randomness. And for the most part, that's kind of true. All right, so the book, The Time Machine by H.G. Wells just says that, okay, this guy goes like way into the future, right? Way into the future where entropy, of our universe is always increasing. So he goes way into the future where entropy of our universe has increased so much that everything is just kind of gray, brown, and boring, all right? Because everything kind of went randomized, all right, within time because of the second law of thermodynamics. So you see, I read this book when I was in high school and I didn't really grasp what entropy was. So I try to sound really smart in my book report, but I don't think it went really well. I don't think I got a very good grade, but maybe that's because the teacher didn't know what entropy was. But that's the themes within this novel. And so the reason entropy was studied so extensively is because scientists, engineers like you were trying to build the most efficient engines. All right, the most efficient engines that would, produce the maximum amount of work, minimize the amount of heat that's produced, so you can get as much work out of your fuel source as possible. So like the Carnot cycle comes out of the ideas of the second law of thermodynamics, and that's what we're going to study here. So first we'll learn how to calculate entropy, and then we'll talk about what it means. So let's calculate it. All right. So again, this is the second law. If the entropy of the universe is more than 0, it's positive, then the process happens. All right. So it is possible. So let's think about that. If the entropy of your system is negative, that's okay as long as the entropy of your surroundings, how that's changing, is very, very big. All right. The whole idea is that sum needs to be positive. All right. So, and just because a reaction is spontaneous does not mean it's fast. So that's a side point that we'll talk about in chapter 11, kinetics. Just because it's spontaneous doesn't mean it's fast. Okay. All right. Oh yeah, and so for a reversible process, so here we're looking at irreversible processes. Universe has to be more than 0. For isothermal processes, it's the same idea. Entropy of the universe actually remains 0. It's constant for those, but again, outside the scope of this class. Okay, so let's think about an example and whether it's spontaneous or not. So let's just use our intuition. We put ice, a piece of ice in our hand. Will it spontaneously melt? Try not to be smart. Just go into your freezer, grab a piece of ice and leave it in your hand. What's going to happen? It's going to melt. Great. Is that an irreversible process? It is. If you leave it in your hand, okay, if you leave it in your hand forever, Will it ever revert back? No, it won't. Yes, you're right that it is reversible, that we could put it back into the freezer and freeze it. But if we kept that ice cube in our hand, it will never refreeze. It's just going to melt and you're just going to have a puddle of water on your hand. Okay, great. So if this is a spontaneous and irreversible process, remember these things are synonymous. What does delta S of the universe have to be? It has to be positive. Okay, so let's prove it. All right, so let's say the ice cube we have is 1 mole. 1 mole of ice, so 18 grams, right? You pull out an 18-gram ice cube out of the freezer. It's initially at 0 degrees Celsius, all right? And we hold it in our warm hand. So let's prove via the second law of thermo that the ice will spontaneously melt. So the energy required to melt ice is related to the enthalpy of fusion of ice, right? We just talked about this, the energy required to melt it. So the enthalpy of fusion for melting ice is 6.1 kilojoules per mole of water, right? And this is the phase change we're doing, solid to liquid, right? So we need to keep track of the heat that's being transferred for these processes and the temperature at which these heat scenarios transfers are happening, all right? So let's call the ice our system, okay? That's our system. And then our hand, we're gonna call that the surroundings. All right, so the temperature of the ice is 0 degrees Celsius. I already told you. That's temperature of ice. The temperature of our hand is about body temperature. So 37 degrees Celsius or 310 degrees Kelvin. All right, so we need to be really careful of our sign. It requires 6,100 joules of energy to melt that ice cube. So Q of the ice, is it positive 6,000 or negative 6,000? The sign super matters. Positive 6,000 or negative 6,000? Negative, positive. It's, yeah, ice, in order to get it to melt, you got to put energy into it. So it is positive 6,000, 6,100, whatever, joules. Okay. Easy numbers, easy numbers. Okay. Okay, so then your hand, where does that ice get the heat? Where does it get it? For free? No, it gets it from the surroundings, your hand. So what is the value of Q hand? 6,000, negative 6,000. Yes, since the ice cube is gaining Q, your hand is losing that Q. All right, so negative 6,100 joules. Okay, sign super important. All right, so the entropy change of both of these processes is Q over T. So the heat being transferred over the temperature at which that happens. So Q of the system for your ice cube is positive 6,100 joules over 273 Kelvin. So we get, did I write this down? Is something like positive 22.3 joule Kelvin. So that's the unit of entropy. It's real weird. Okay, joule Kelvin. All right, so the same thing for entropy of the surroundings, it's Q over temperature at which it happens. So again, sign super important. Negative 6,100 joules over the temperature of your hand, which is 310 Kelvin. And so that value equals negative 19.7 joule Kelvin. All right, so that is the entropy change of your hand. All right, and so the universe is your ice cube and your hand. All right, so the entropy of your universe is going to be equal to positive 22.3 minus 19.7. What is that? It is greater than 0. So does this process happen spontaneously? Yes, it does. And so the interesting thing would be, you know, you could swap the numbers. I could say, oh, the ice loses 6,000 joules. The hand gains 1,000 joules. So your 6,000 joules, you're trying to say, oh, the ice cube heats up your hand. Does that make sense? No, that does not make sense. You can prove it via the second law of thermo, that if you swap the signs, you'll get entropy of the universe is negative. You can't have that. So that would never happen. Heat will never transfer from cold to hot, and it's because of the second law. And I think that's really cool. I don't know, but I think that's pretty cool. Okay. All right, so let's talk about what entropy is. Entropy is not disorder. Disordered helps us kind of, understand the relative magnitudes of entropy for different systems, but it doesn't give us a mathematical way to measure it. So entropy is about related to probability, okay, statistical mechanics, and understanding how many different microstates for a system, for a sample, how many different ways can you arrange the particles in your sample and still have the same energy of sample, all right? That's essentially what entropy is, microstates. So what a microstate is, so let's look at this picture, all right? We have some gas particles here, all right? And the valve is closed, okay? So basically the particles can only live over here. What if we open the valve? What's gonna happen? Can you predict what's gonna happen? There's a number of possible things that could happen, right? You open the valve, right? Let's draw this. Actually, let me just go to this picture. Okay, so there's the valve is closed. So when we open the valve and we gain access to the other side of this container, the particles, there's a number of things that can happen. The particles, they can stay on the same side. That is a possibility, right? Or both particles could go on the other side. That's another possibility. Or, the red one can go over, the blue one can stay on one side, or like swap it the other way. So there's 4 different possibilities that those gas particles could go. You could, take a picture of that open valve at any point and you have equal, 25% chance of seeing any one of these pictures. So a microstate is a possible arrangement of particles that results in the same energy of that sample. So how many microstates are present in this picture? There's only one way that those particles can be arranged, right? Those particles cannot go on this side, right? They can't get over that barrier of the valve. But over here, how many microstates are here? How many possible arrangements? 4. All right. So the trend here is that number of microstates that increase, all right, your entropy increases. The more possible arrangements you have in the sample that result in the same energy means that sample has more microstates, right? So the idea here is like, think about a solid sample, right? All the particles are really, really packed close together, right? Those particles can't really move that much. If you would move one of these particles away, you would be really changing your sample. Okay, if you move particles in a solid, versus if we had a gas and all those particles are just kind of enclosed in a container. If I moved this gas particle, over here, is it going to change the sample that much? No, those gas particles are bouncing off the wall like crazy idiots anyway. It's not going to make a big difference. So gases have a lot more entropy than solids because of particle arrangements. And that's another factor in entropy. So I want you to be thinking about microstates, possible arrangements of particles, right? Again, be very, very careful with this definition. Entropy is disorder. Entropy is a level or a measure of randomness. It's kind of wrong a little bit, all right? If you go onto the physics memes subreddit, there's always jokes about entropy and dirty. Actually, no, if you read the New York Times or any comic and they try to relate to scientists, they always use these entropy jokes, all right? Okay, so it's oh, a kid is dirty. And why do you explain the entropy? Okay, that's what explains the dirty room, all right? Oh, dirty laundry, entropy, dirty dishes, entropy, all right? And that's the joke. But again, it's a little bit wrong, all right? So think about it in terms of microstates. Okay, this is fine. This is fine. Ranking this on terms of entropy. Which bedroom has the most entropy? 1, 2, or 3? The third one. It does. It does. The third one does, in fact, have the most entropy. I Googled levels of hoarding. That's where I got these pictures. Okay, so how do we relate this to microstates? So if you just think, oh yeah, entropy is disorder, you would get this question right. The room on the very right is the most disordered, has the most entropy. But here's another way to think about it. Pretend this is your room. This one's your room, and you, or no. Okay, this is your sibling's room. Someone you want to annoy. Okay, that's their room, and you want to go in there and mess up their room a little bit. Okay, what if you moved that pillow like a little bit? You wanted to mess with them. Do you think they would notice if you moved their pillow? Yeah, they would notice. So moving that object gives you a different macro state, meaning that you don't have a lot of microstates in this picture. You can't rearrange anything and your roommate not notice. Okay, but what about the second picture? What happens if you would move that pillow? Do you think they would notice? Maybe if they were neurotic, okay, they would notice. Okay, so the second picture has way more microstates that you could move that pillow. You're not changing the overall messiness, the overall energy of that system. Okay, and so your roommate's not going to notice. But what about the third picture? And you try to move that pillow. What pillow? Right? So in this case, you move that pillow, yeah, your roommate's not going to notice. It's under a bunch of stuff. Okay, they're not going to notice. So here is an example of a picture that has tons of microstates that all yield the same macro state, right? You could rearrange, you could, swap some items of clothes. It's still a really messy room. Okay, does that make sense? Yeah, that's where microstates come in. Okay, so let's do another one. Is entropy, so do you believe me, entropy is not disorder? It's not disorder. It'll get you in trouble, I promise. So let's look at these two bathrooms. Kim Kardashian's very sterile bathroom or a normal person bathroom. Which one seems more if we do it, let's do it wrong first. Entropy's disorder. Which bathroom seems more cluttered? Kim's bathroom or a normal person bathroom? Which one seems more cluttered? The normal one, doesn't it? Yeah, the normal one. But that's wrong. That's wrong. The bathroom that has more entropy is actually Kim Kardashian's bathroom. Okay, and here's the reason. Use the idea of microstates. If I moved this bathroom vanity, the sink, 3 feet into the middle of the room, is it still a functional bathroom? If I moved it in the middle here, if I put the sink right here, I called up a contractor, paid $5,000 to move it in the middle of the room, is it still a functional bathroom? Not really. But what if you took Kim Kardashian's bathroom and you moved this sink 2 feet to the right? Is it still a functional bathroom? Yeah, it is. It is. If I move that tub a couple feet, it's not going to make a big difference. It's still going to be a bathroom. All right. So in this example, Kim Kardashian's bathroom has many more microstates because you can move those fixtures all around, okay, all around, and it's still a functional bathroom. But there's not many different places in the normal person bathroom that you could move those fixtures and it still work. So what factor led to the difference in entropy here? The space or the volume? Yes. So volume is a factor in entropy. Okay. And so the real one is Kim's bathroom. Okay. Kim Kardashian's bathroom has more entropy. That's the right answer. But when you saw these pictures, which one did you think had more entropy, or did you not know? Or did you not care? Not care. Okay. All right. Just lie to me, please. So yes, it is. Kim's is more entropy because it's more spacious. All right. And so here are the different factors that relate to entropy. Volume is one of them. All right. That if you let's pretend we have a gas sample. If we have a gas sample and there's tons of room for the gas samples to occupy, you can cut and paste those gas particles anywhere and still have the same entropy, versus if they're all crammed in a tiny, tiny space, there's less positions you can put those gas particles. So volume is a factor where increase in volume gives you increase in entropy. So all of these things increase entropy. All right. If you increase the temperature of your sample, that increases entropy. Why do you think? They're like space, they're moving around more. Yeah, they're just going crazy. Yeah. Okay. All right. So increased number of molecules, right? Again, more microstates because there's more molecules that you can move around, right, will give you more entropy. Increasing the complexity of a molecule also will increase your entropy. If you just have a helium atom versus like a nitrogen, diatomic nitrogen molecule, nitrogen has more entropy than just an atom. And the reason is chemical bonds. Also, if we look at like water, see how water has 2 chemical bonds or like, yeah, covalent bonds here. If the more bonds you have in a molecule, the more vibrations that each particle can do. And so if there's vibrations, there's another mode of disorder that you can bring into your sample. So here, water would have the most entropy because it has the most bonds. There's more vibrations that can happen. Okay, particles will move through space, gas particles move through space, but if they're vibrating also, that's more entropy, right? And then the last one here is molar mass increases will also increase entropy. Okay, so let's do it real quick. I bet you're real good at this. Pick the higher item, the item that has the higher entropy, and state why. A or B, the first one. Liquid water at 20 or 50 degrees Celsius, which one has more entropy? B, okay. Liquid water at 100 degrees Celsius or gaseous water at 100 degrees Celsius? Gas, yes. Nitrogen gas or helium gas? Nitrogen. All right, 1 mole of helium in 1 liter or 1 mole of helium in 5 liters? 5 liters. Helium or argon? Argon, yeah, you scroll back up. What was another one of the factors? Molar mass, weight, so argon. 1 mole of neon in 1 liter or 5 moles of neon in 1 liter? Number of molecules in a space. So it'd be 5. All right. This one's the last one, the tough one. CH2Cl2. So this is a carbon atom that's tetrahedral. All right. So both of these are tetrahedral. CH2Cl2 or CCl4? This one's tough. A or B? B? So you might say B if you think it's molar mass, but think about how these differs. These both have bonds in them, but the chemical bonds in CCl4, they're all identical, right? All of those vibrations are identical, but in this one, you have 2 that are with hydrogens, 2 are with chlorine, so actually this one. Okay. So we'll review that when we come back from spring break because you're all gonna forget. All right, so do you have a good break? I moved your homework to Tuesday instead to give you an extra day. So yeah, if you're turn in your notebooks, we will not extend the notebook thing, but the post labs are extended another additional week. But do check the assignments on Carmen. But notebooks are not extended. Those have to be handed. What email?
The horse.
Oh. I want to encourage you. Was that encouraging? Keep up the good work.
I'm not even like, no, my original plan was to try my name. My original plan was to try my name.
Yeah, you too. Don't forget everything, please. Oh yeah, what's up? Okay. Okay, you can. Probably not, but if you can talk to me, so after break, so let's all take a good break and then come back refreshed, all right? And then starting when we get back, why don't you send me sometimes you are available and you can sit down for like an hour and get caught up on
exactly.
Okay. Oh, so you're good like after class meeting.
Yeah.
Okay, then okay, we can do that after class.
Yeah.
Or we'll get back. What's up?
What chapters is it in cover?
I think it's gonna cover 8, 9, or sorry, yeah, 8, 9, and 10, and I think we're gonna do 11 too. Yeah, so we're actually deviating a little bit from the syllabus, but we already did because 8 was supposed to be on midterm 2, but I thought it was too much. Yep, you too. Because not everything's taken again. Oh, am I still recording?